actually the approximate solution, which will be approximately equal to 0. So that is why we are saying that this is my differential equation. Now please note that this time my differential equation has not got the y term as I had in the first example. If I have the y term, if let's say y double dash plus y plus f of x, then that y will give me the mass matrix. But here I have only y double dash plus f of x, so I will only get the stiffness matrix. Okay, so I have I is equal to 1 to m plus 1 and the double derivative and yi ni. So this is now very obvious. Yes, I have substituted the definition of y tilde y steric here, the linear combination of the y values and the basis functions plus f of x, right? So now students, we can see that we can have the integration on both sides, just as I discussed earlier, and I've showed you the detailed derivation. So you will be able to find the solution. Now we will apply it, implement it on a problem in a minute. But before I go to that, I want to show you that if I am talking about one segment, then you will get numerical. This is the actual graph. The thick line is the actual function, and you can see that the numerical approximation is very, very bad. If I'm using one segment, if I'm using two segments, the numerical approximation is something like this, which is almost approximating the graph. But if I'm using 4 segments, it is much better, right? So now, in the light of these equations, we observe that in any interval, only 2 of the trial functions are non-zero. Taking this observation into account, equation 5.14 can be expressed as this. Now you can write it on your notebook. This is just the simplified version of equation, and 5.15 is the most important equation to find the stiffness matrix. Okay, this is the generalized representation of stiffness matrix, and this F stands for capital F, stands for F vector. Okay, now you have we have already discussed the basis. Okay, so now here we have just discussed the special cases when n1 is 1, n2 is 0, n1 is 0, n2 is 1. So you can also go through this slide in detail and then you can explore it further. So now you can see that we can write, for example, if I have only n1 and n2, then I can always substitute ye here, yj n1 plus yj plus 1 n2, right? So now students, let us go to a problem, right? So in short, like when you are talking about the Galerkin weighted residual criterion, you can find this result. Okay, and then of course, as I taught you earlier, the integration by parts, and then remember that it has got 2 representations. After evaluation of the non-integral term and rearranging is equivalent to 2 equations. What is the difference in these 2 equations? You can spot out easily: n1 and n2, integral of the same thing with n1 and then with n2. Okay, so please remember that. So now note that in arriving at this form 5.26, explicit use has been made of equation 5.2.1. Okay, so now please go through these 3 important points. I can ask you in the viva, what are the 3 benefits? These 3 benefits are: the highest order of the derivative appearing in the element equation has been reduced by 1. For example, if I had y triple derivative, what will you do? You'll do the integration by parts and you'll get y double dash. Similarly, I had y double dash, so it is reduced to y dash. As will be observed explicitly, the stiffness matrix was made symmetric if we did not integrate by parts. One of the trial functions in each equation would be differentiated twice and the other trial function not differentiated at all. Next, integration by parts introduces the gradient boundary conditions at the element nodes. The physical significance of the gradient boundary conditions becomes apparent in the subsequent physical applications. All right. So remember, students, please write on your notebook 5.26 and 5.27 because we are going to now use these equations to solve a problem. Okay, and then we can write it, the equations 5.27a, 5.27b in the standard form like this: k K1, K1 2, K2 1, K2 2. And remember that these Ks are nothing but the integration of Ni and Nj on Ni's derivative, Nj's derivative on the given interval. Okay, so now this is an example. Now let me show you quickly the example of spring, how we connect the things together. So let me take you to this example and another one here. Right, so I will give you another task, maybe near the terminal, because we've already gone through the midterm. So I just want to show you that if we want to combine the elements, what will happen? They will be connected like element by element. When you work, you can combine these elements and you can make a bigger matrix. Okay, something like, let me show you the projection here. Right, so you can always make a bigger matrix with the help of the smaller matrices. Okay, so this is a very important point that you need to keep in mind. So this is another example. I will share it with you later. Okay, but let us go back to the slides. Right, so now let us go to the task. Use Galerkin method to formulate a linear finite element for solving the differential equation. Now you can see this time I have this differential equation, and the very nice thing is that y double dash plus y, no, y double dash plus y dash. Okay, so we will treat it differently. Right, subject to y of 1 and y of 2 is equal to 0. First, note that the differential equation is equivalent to this, right? So we have now simplified or modified this differential equation, which after two direct integrations and application of the boundary conditions, the analytic answer is given here. Okay, now for the numerical solution, for finite element solution, the simplest approach is to use a two-node element for which the element solution is assumed to be like this. Okay, now I've already defined n1 and n2 different definitions. Okay, so this must be in your mind, and this is how we use the interpolation. So then y1 and y2 are the nodal values. The residual equation is given as this. Remember that this time this equation is different. Okay, so you will have a different way of integration. Right, so now after integration by parts and after simplification, we will be left with the stiffness matrix like this. Okay, now it depends on x2, x1. Now what about the patches? How many patches were there, and what was the starting point and what was the ending point? X naught or a is 1 and xn or b is 2. All right, so now we will say that we will illustrate two element solution is formulated by equally spaced nodes at 1, 1.5 and 2. Okay, now I have divided it into two patches, 3 points. Okay, so now I will work for the now you can see that what is this capital F? The capital F stands for the integration on the other side for f of x. Okay, so in this example, what was f of x? F of x was 4x, right? Minus 4x. So now you will use it minus 4x and then you will multiply it as we did with n1 and n2. Let me show you. We had a multiplication here. Can you see n1 times f of x, n2 times f of x? So now we are working on this part. So here you are getting n1 times f of x, n2 times f of x for the first element, n1 times f of x, n2 times f of x for the second element. The element equations are then written in this form. All right, And now what is this capital Y? Do not be afraid of this capital Y. These are the functional values at 1, 1.5 and 2, and we will work on it with the help of the boundary condition. Y1 and Y3 is given to you 0, which is good. And then from the analytic answer we can find Y2, of course, and then these values you can obtain easily. And then what is happening here, students, actually I have now assembled it, and now can you see here, this is a more you can say that finer grid. Okay, now I have now reduced the step size to 0.25, 1, 1.25, 1.5, 1.75, and 2. And I have got the tri-diagonal matrix, just as we did in FTM. Similarly, again in FEM, we have got a tri-diagonal matrix, and the reason is that at the boundaries I had 0, so that's why it happened. Okay, it is not always the case. Okay, and you can also see that this matrix is symmetric or not. Can you please tell me?